Hello everyone, welcome back to another week of Learning Glass studio session. Today we'll talk about measurements and how we can quantify the uncertainty of our experimental measurements and also use the experimental measurement error that we have, and then when we use it to calculate a different value based on our measurements, how that works in terms of keeping proper experimental error propagated throughout these calculations. That's what the propagation means. It means that you take a measurement of some value, some property, and many times in science and engineering, that value or property is used in analysis, in calculations to find other properties based on, you put these values together in equations. So there's a whole process on how to properly use the measurement error from one raw value that gets analyzed and processed to find other values. That's what the propagation of uncertainty is. So a way to start this discussion would be it's basically an example of how this can come up. So discrepancy, has to do with measurements as well. And when this topic of discrepancy is important because if you're trying to use measurements to answer a question, it's always one of the things to ask is how does this measurement I'm taking fit into either other measurements that have been done, other measurements that I have done, or comparison to an accepted value. That can be discussed in terms of discrepancy, meaning if I have a certain value, how does this compare to other values? And that's quantified by taking the difference, by subtracting them between each other. So difference between two measured values or measured and accepted values two measured values of the same quantity. So if you look at the same thing and in one experiment I do this measurement twice, what is the discrepancy between these two measurements? Or I do this measurement once, someone else does this measurement once, what is the discrepancy? Or I use two different tools for the same measurement, what is the discrepancy? Or how does this compare to the expected or accepted value? And so like another way of saying it, what is the disagreement? And you quantify that by subtracting them from one another. So that is can be, you can think of many examples of that, but let's talk about measuring in resistance. So if you have a ohm meter, resistance meter, let's say that this ohm meter has a scale that you would read of resistance in the units of ohms. Let's say that person A person A, I guess, would be here. Let's say person A gets a value of about 15 ohms, but in their measurement uncertainty, they properly report their best estimate and some range of uncertainty, plus or minus. Another student takes the same quantity, the same circuit, but they get a different value with this uncertainty. So in this case, the discrepancy here would be 25 minus 15, so it'll be 10 ohms is their discrepancy here. Okay, a different situation could occur where, let's say it's the same circuit, the same chart here, and the students get the same value. So let's say Student C also gets 15 ohms, but the uncertainty is imprecise. They have a very big error bar. And student D gets 25, and they have a big error bar as well. So these two students have bad measurement techniques, but they get the same numbers. And here you can see that the discrepancy is also 10 ohms. This is a discrepancy. This is discrepancy of 10 ohms. So here is two situations where because of the experimental uncertainty, you have the same discrepancy between measurements, but it's a very different situation. What is the difference? It's that this difference here is more conclusive in terms of not what the true value is, but it definitely tells you that someone did something wrong. So this is significant discrepancy. The difference is real. It's because the discrepancy is bigger than the error bar. And so what you conclude here is that at least one of the measurements is wrong. So they might be precise, they give a small error bar, but something is wrong with the measure. Assuming the error bar is correct and they're reasonable reports of the error bar, one of these measurements is wrong, because the difference is bigger than their error bar. But biologically, you can also see that this has good and bad things. The good thing is that both are right. That's the good thing. So this is insignificant error. Insignificant discrepancy. Insignificant discrepancy. Significant discrepancy here. And this is because the discrepancy is smaller than the error bar. So both could be right. So that's the good thing. Both of them could be right. The bad thing is that it's imprecise. Their error bar is too big. So the error bar is basically the same magnitude as their value. So this is 25 with an error bar of like 10. This is 15 with an error bar. So it's like a error is a big chunk of their percent. It's more than 50% of their actual value. But what you can say is that their discrepancy, the difference between these measurements, isn't big relative to their error. So they could basically be telling you the same value, and that's because their whole measurement is fuzzy. A difference of 10 is not that much compared to their error bar. So those are two examples, and of course what they did there was to find the discrepancy. They said discrepancy D equals the measurement from student A minus the measurement from student B. So the question is, what is the error bar of the discrepancy? Each of these measurements, so Well, discrepancy, so I'll go back to this here, but I guess let's make some room. I'll make some room here. So it applies to X, measurement A and measurement B, but for this example, let's go to this side, measurement C and measurement D. So measurement D minus measurement C is the discrepancy between the two. So the question is, what is the error bar on this? And we'll describe this on terms of this graph here. So we have these error bars. Well, one way to think about it is the maximum error, or the maximum value based on this error bars, the max discrepancy is if somehow during this measurement, if you're within this range, that D takes on a value at the top of the error, and C takes on the value at the bottom of the error. So in that case, this is plus sigma D. This is minus sigma D. So C, the error in the C. But if you take the magnitude, this is one chunk. This is so if we're taking the difference between if you were to take this value minus that value, that would be a big discrepancy. That would be one possibility. So that would be the error, the maximum error would be the error due to sigma C plus you add on the error due to sigma C. So that would give you the biggest range of possible values. And then you take the difference from those, that would be the most. Then, if you take it to be, so that basically gives you the maximum possibility. And minus and minus, that'll be another story. But the point is here that it's going to be at least somewhere in there. So the maximum discrepancy for some, even though we subtracted these values, when you do this operation of one minus the other, the error does not decrease, the error increases, because it could potentially be something this wide that started, the original values are this wide and this wide, but once you take the difference, you increase the range of possibilities in terms of the error uncertainty. So the maximum case for, let's say in general, some value Q, it will be so if you were, let's first define what we're doing. So in general, if you were to say some value Q with some measurement uncertainty, sigma Q, is based on two measurements, XA plus or minus sigma XA minus another measurement, so that's the question we're trying to ask. What's the uncertainty once you do this operation based on measurements? Well, from this graph example we had, the max I'm saying max because I'm going to tell you that we can reduce this. We can use a theory to reduce this, but it definitely falls within this range here of the errors adding up to each other. So because you did this operation, even though you're subtracting these two values, the uncertainty adds rather than subtracting. But without showing you guys the theory, I'll show you a general rule that if you can argue, so this is valid, the error is always going to be within this range here, but you can narrow this range if you apply the theory of random error, saying that there's no systematic error and it's just the best we can do, and this is just due to all these unforeseen circumstances adding up that are not systematic. A theory says that for whenever you subtract two values, the uncertainty of that difference, it still adds up, but it's a little bit smaller. Instead of adding them directly, you take the square of the sum of squares. So this is slightly smaller. This is bigger than that. And it gives you a little bit more precision if you're applying a theory based on random error. So we're not going to discuss how that happens, but now this is the solid rule here. This is the rule. When you have two measurements and you take the difference between those measurements, the resulting error you get from that operation, that subtraction operation, is you take the square, you square each of those uncertainties, and then you add them up, and then you take the square root. So that's a rule for both addition and subtraction. And so that's why you would propagate the error when you take the difference from two measurements. So that's one example. And that example came up for this practice of discrepancy, which is important for experiments. Like I said, that discrepancy can be between two different runs of an experiment that you did. It can be comparing two different experimental results between two different people. It can be results between two different tools, or it can be results between an accepted value and or expected value and your experiment. Okay? So, as we said here, that this is significant and this is insignificant, and it all depends on the error bars. And this one had pros and cons. And one of the cons was that it was imprecise. So, how do we describe? We can put a number on the precision, and it has a few different names. For example, fractional uncertainty is one name. You could also call it relative uncertainty. Another name is precision. How precise is this measurement? You can put a number on that, and what that number is saying that if you have measurements that you report for a measurement which is, if you do your measurement right, you have to report both your best value that you can determine, put a number on, plus or minus some error in that measurement. And starting from here, you can put a number on this precision, which is given these different names, and the number you put on it is the absolute value that you determine for this measurement divided by the magnitude of that measurement. So here we can put a number on how precise these measurements are. So on this scale, we see that the magnitude of these measurements is either 25 or 15, same thing here, 25 or 15, but one is more precise. These students are less precise than these students. So to put a number on it, it would be the precision here for B would be, for B, it would be the uncertainty of B over the value of B, the best value for B. Let's say, just for my eyeballs, it's 25 is the denominator over, let's say, that's like 3. So it would be the uncertainty of plus or minus 3 ohms divided by the value of ohm that they report. So that's like 3 over 25, that's less than 1/5. Maybe that's 1/8, 1/8-ish. So that's like 10%, 0.1. Just putting a number, eyeball the scale. And with A, it's a little bit higher because you have a similar uncertainty bar, error bar, but the value in the denominator is smaller. So for A, let's say that's 3 over 15. So that's 1/5, so like 20%. So those are more precise, which is still not very precise. 10% precision is not that good. But this is even worse. We can see that for the precision, here it is 25 for student D, 25 divided by pretty much like 12, let's say it's a half. 25 divided by 12-ish. So that's about 50%. Just putting an imprecise number on this calculation. That's about 50% precision, which is bad. Here is probably worse because it's the same error bar, but a smaller value. So that would be 15 over 12. That is, oh wait, what am I doing? Should be the other way around. 12 over 15. So that's basically, if we divide this by 3, this would be 4/5. So 80% error, which is huge, which makes these measurements very inconclusive. It's still an example of insignificant discrepancy, but it's a very imprecise number and it's inconclusive. So that's precision. And it's an example of fractional uncertainty, which we're going to use to help us define different operations. So that comes up, that helps us with making another rule. So we haven't multiplied two values together yet, but we'll do that next, and we're going to use this concept of the fractional uncertainty, the concept of the precision. So if we have this measurement, the next question is, what do we do when we multiply two measurements? How does that affect the experimental uncertainty of the product, the result from multiplying? So that has another rule to it that help us to keep track of this measurement error when we start to process it, when we start to use it for analysis. Okay, so multiplying two measurements. Which we can imagine happens a lot when we're doing our engineering analysis. So another way to write this best estimate, we can write this in terms of the precision. So that another way to write this would be if this is the definition of precision, we can say that x best is this plus the fractional plus the precision. Yeah. That's another way of writing this in terms of the precision. So that'll help us to get a general rule on how to keep track of this uncertainty when we have two measurements and we multiply them. So for one example would be using experiments to calculate momentum. So if you may remember from high school physics or physics 1 and 2, the momentum of a body is defined as P, and it's the product of the mass of that system or the mass of that body times the velocity of that system. Here's an example in engineering and physics where we need to multiply two values, and if we measure these two values, those two measurements have experimental uncertainty, measurement error. The question is, what happens to that measurement error when you use this measurements to find momentum? So that's an example of this multiplication. So let's apply this form of the measurements to see what happens. So the measured momentum will be based on other measurements, so it will become its own best estimate because it's based on measurements. It's the product of these other two best measurements. You have a best estimate of the mass, and to do this properly experiment, you have to report your measurement uncertainty of the mass, and same thing with the velocity. You have this best measurement of the velocity, and it comes with this measurement uncertainty. Okay? I should have wrote it in this form, but I guess this is a good reminder. So I'll write this over here. Oh, no. So that's how but if we write it in the fractional form, the best measurements come out here, and the uncertainties look like this. So that's applying this definition of the precision. So by looking at this, the biggest possible number that you can get from here, oh, this would be plus or minus. Just by inspection, if you the maximum number you'll get is if both of these are added, and the smallest number you get is if both of these are subtracted. So you apply the plus sign to get a big number, you apply the minus sign to get the smallest number. So the max P best is plus if those uncertainties are added to that, you'll get a bigger number. And similarly, the minimum p-best value from these measurements is if you take the same best measurement numbers, and then, but when you report the uncertainty, you subtract to get a smaller number. So that's the range, the minimum and the maximum. So if you were to, so the result of this would be that the full range can occur when the distance between these, so by looking at that, what the result is that in general, or not in general, but so that the keeping in mind what the maximum would be and the minimum would be, the distance between those is the same as saying that this best measurement in this case, when you, which is this equation, is multiplying the two measured values together, is the uncertainty from doing that is 1 plus or minus these fractional uncertainties added together. So you add these together, and then that's the plus or minus that you're going to use to define your measurement uncertainty. So that's how it works in this case. So we can write that into a rule based on the fractional uncertainty. So we first had a rule for subtracting or addition. It's the same thing. Adding or subtracting is the same thing in terms of what we do. We take the squares, sum of the squares. Sum of the squares, square root of the sum of the squares. Then, for multiplying, we worked out an example here, but in general, we can say for the largest error, similar to here, largest error, the max error, in this case, when we're for Q equals X times Y times Z, the largest Q that can come from this would be, in terms of fractional uncertainty, would be the sum of all the fractional uncertainties that you measured. So these dots mean that it's a pattern. It just keeps on going on. You multiply one, you keep on, that's what this equation is. You just multiply each of these values by each other. And if that's an equation you're using, the largest uncertainty you can get, and which is a good conservative thing, it covers all your bases, would be all the fractional uncertainties added to each other, the largest fractional uncertainty. So, but again, for random error, which we can use to say that our errors are just from imperfections of our universe, that we try our best, we try to be careful. There's no systematic reason why there's an uncertainty here. It's just a limitation of our measurements, our eyeballs, our tools. All of that can be considered random. In that case, the fractional uncertainty from that in this equation would be the square root of the squares, sum of all the squares. So that's how the random error would propagate for this equation. If you were to use measurements with their reported uncertainties, when you have to multiply out them all each other to get a new value, the error would propagate such that the fractional uncertainty is that. You would take the fractional uncertainty of one measurement, square it, add it to the next one, square it, add it to the next one, square it, and then once you have that sum, you take the square root of that whole thing. It's similar to this, but it's a little bit smaller. And that's due to you can make it a little bit smaller if you can claim that it's a random error. Okay, so skipping a few steps, we can now introduce the granddaddy equation, which covers all bases, covers all equations. So there's two cases we talked about, taking the difference between two measurements. That's discrepancy is one time when you do that. Taking the product of two measurements, momentum is one example of that. And we use those examples to come up with these general rules on how this propagation of error is carried out, because those measurements have experimental uncertainty. So the question is, if you're using those measurements in an analysis, how does a result of your analysis, what is the experimental error of the result of your analysis? Because you don't measure those results of the analysis, but you use measurements to find something useful, which is what a lot of experiments are doing. So there's a general rule which works for all equations. And spoiler alert, there's calculus involved. So that's cool. Finally get to use our calculus skills. Okay, I might finish erasing someday. All right. So the general rule for any equation using measured values. For example, some quantity Q, which is a function of many measured values, x through z, which can be any number, each of those having their, measured best value plus or minus some uncertainty. Should be a subscript. Each of these x through z has their uncertainty. What you would do is the absolute uncertainty of this resulting value is equal to this granddaddy equation. What is that granddaddy? It's the partial derivative of this function with respect to the certain measured value in this equation. Then you multiply it by the uncertainty in the measured value. So So let me try to make these a little clearer. So this is partial derivatives. It's delta, not sigma. And you take that product and you square it, then you go down the line for each of the variables. There's this equation Q, it's a function of many different variables, and you take the partial derivative of each one and you multiply it by its uncertainty. And then you take the sum of all those squares, and then you take the square root of that. So this this is the partial derivative of Q in X. So there's an equation Q that has a variable X, and you look for all the X's and you analyze the derivatives of that, keeping everything else constant. And this delta X is the measurement uncertainty of X. So you identify each of these for each variable in the equation and you go about it. So here's an example. So let me erase all this stuff. So this works for all equations. So you can apply this to subtraction, you can apply it to multiplication. It'll give you the same answer as these here, but it's more general. It'll work for all equations. So in this multiplication case, you would take the partial derivative of the momentum with respect to mass, take the partial derivative of momentum with respect to velocity, and though the result of that is a new equation, then you would plug in the numbers of your measurements to that equation, and then you multiply that by its the measurement uncertainty, then you square that, and then you add it to everything else, and then you take the square root of that. So that's how the verbal algorithm is, but I'll show you guys an example of a specific measurement we're doing and using that to find the result, and then have an error that propagates from the measurements. Okay, so what example can we have? I was trying to find one. I found a pretty cool one in terms of, not found, but I created a cool example, which has to do with an everyday situation when we ask ourselves, if I had a donut, what is the volume of this said donut? So let's say this donut looks like this. That's the donut hole, and this is the donut here, and this donut has a certain volume, and if we're doing an experiment, we can say, well, this donut kind of can be modeled as a cylinder with a hole in it, three-dimensional cylinder with a hole. So we can say that, okay, if we can measure the height of this donut, and if we can measure the diameter of the hole, let's call this little d, and if we can measure the diameter of this this bigger ring, call this big D, we can get the volume of the donut. So in this case, the equation we're using is the volume of this donut, and let's call this the variable V. So what we're doing here is we're saying, what is the volume of the donut? It's going to be a function of big D, little d, and h. Those are the measurements we're going to take to find the volume of this donut. So specifically, the model is the volume of the donut equals the area of this ring, which is the difference between those, it's a concentric circles. So the volume of the cross-section of a circle is pi over 4 d squared, but we're taking the difference of them because there's a hole. Then we multiply it by the height. So that's the volume of a donut based on the diameters and the height. So this is any equation, our equation of this, and to find the answer, we need to measure d, little d, and h. So that's what we're going to apply this general propagation of error equation to. Okay? So from this equation, what we have to do is find the proper partial derivatives with each variable, find use the reported, I'm going to tell you I'm going to report those right now, measurement uncertainty for each variable, and then we're going to square them and sum them and take the square root. So given, we go in the lab, we take our donut calipers, and we take measurements of big D, little d, and h, and what we got was that our D best of the outer ring is 5 centimeters plus or minus 0.1 centimeter. So that's our D best measurement. Our little d best of the hole, it's 1 centimeter. It's a little harder to measure, so we have a bigger uncertainty. And the h, it's also 1 centimeter, but it's even harder to measure for some reason, so it has a bigger uncertainty. So that's our D best values, and then this is our uncertainty. So this would be our best plus sigma best, delta best, okay? So these plus or minuses is what we plug into this side here. Now we have to find the partial derivative of our function with each of these variables. Here there's 3 of them. Okay, so let's do that. So the partial derivative of v of the donut function with respect to d. Anyone doing that at home? So you take this function to remind you of calculus. What partial derivative is you have this function of 3 variables, and the partial derivative of d is only saying that this is the variable, everything else is constant. So if that's the case, the h becomes a constant, pi over 4 is a constant. If this is a constant, so it's the partial derivative with respect to d of this function, which I'll separate out for you guys. Pi over 4h d squared minus pi over 4h d squared. That's v. Okay, so assuming when you take the partial derivative, everything else is constant. So this is a constant, this whole thing, h is constant, d squared is constant, these numbers are constant. So if that's the case, the derivative of this is 0. That goes to 0. The derivative of this is this constant times the derivative of d squared. What's the derivative of d squared with respect to d? 2d. So this is 0, and you get a new function equals pi over 4 times h times 2d. That's the partial derivative of volume of the donut with respect to big D. The partial derivative of the donut expression for little d is similar. The only difference is that if this is little d now, this is the constant. This we have to do a derivative on. The difference is here there's a negative. So that's going to be negative pi over 4 h times 2 little d. That's the partial derivative of that. But when we're talking about h, it's different as well, because now all of this is the constant, and we need to take the derivative of that. The derivative of h with respect to h is 1. So dv donut, I'll do that a little here. So these are the three new equations. When you take the partial derivative of an expression, you get another expression. You get another equation. So that's the new equations. Then we plug in the numbers to here, where h is our best value of h, big D is our best value of big D, and we plug those in to get a number for this partial derivative. So this is the equation. Now we can plug in the numbers. So this would be pi over 4 times 1 times 2d, which is 5, which is 2.5 pi. Plug in the numbers here, you get pi over 4 times 25, 5 squared, minus 1 squared, times 1. So that equals 6 pi. Here, you plug in the numbers. It's negative pi over 4 times 1 times 2 times 1. That gives you pi over 2. So those are the numbers that we're going to plug into each of these sections. Then we're going to use the reported experimental uncertainties and plug them into here. So we're almost ready to get a number out of this propagation of errors. Okay, so let's do it. We're going to use our engineering skills to get the volume of the donut and then report the experimental uncertainty based on our measurements. So it's going to be the square root of the partial derivative of each variable times its experimental uncertainty. So in this case, it's going to be the square root of all these sum of these squares, which would be let's start with this big D. Big D, this is the partial derivative of big D. and this is the reported measurement uncertainty of big D. So that would be 2.5 pi times 0.1 centimeter. And that's going to be squared. Plus, let's talk about little d. Negative pi over 2, there should be negative here. Times 0.2 is an error. Then you take the square of that. Plus 6 pi times the uncertainty of that, 0.3, this h variable. Then you take the square of that. So that's the number. We took the partial derivatives, got a number for that by applying these measurement values. We multiply that by the experimental error. We do that across each one. We take the square of each one, and then we get a number. Then we take the square root of that whole thing. When you do that, I got 5.7 centimeter cubed, because this is a cube, because this is a d squared, so this is a centimeter squared multiplied by a centimeter. At the end, you should get centimeter cubed. So I got 5.7 centimeter cubed. And if you're doing this at home, if you apply our measurement values to this equation, you should get 18.8. It's 5 squared minus 1 squared, that's 24, times 1, which is the height, times pi divided by 4, that's 18.8. So our measurement of the volume of a donut is the volume of the donut best is 18.8, which is when you multiply those measurements together, plus or minus 5.7 centimeter cubed, which is a big error. So if you do the precision on this, this is about a 30% precision. So that's the answer. And then think about it a little bit more. 30% precision, 6 centimeter cubed out of these values here. But that's what happens when you take powers. When you take exponential values, or you square it, or you cube it, these errors propagate a lot if you cube it and such. If you have starting from one experimental error and you use that in the square of an equation, that's when they propagate into these big errors. But at the same time, we started off with big errors. This is about a 5% error. This is a 20% error. This is a 30% error. So we started off with imprecise values. And so it's not surprising when we take our final result, we also have a big error of 30%. Okay, so that's all I had today. We're going to use this in our class on our lab reports and our measurements. So keep an eye out for that. We'll talk more about this when we have our specific situations. Okay, so see you next time.